We've just learned about the basic parts of an airplane and how it is controlled, but it's equally as important for us to understand how the power is generated to move the airplane through the air. An airplane has an engine, which is commonly referred to as a power plant. The reason behind this name is simple. The engine not only powers the airplane to move it through the air, it also has other components attached to it in order to create electricity, vacuum suction, and heat, just to name a few. The power plant of an airplane, like an engine of a car, is one of the most important components because without it, there is no way to get the plane off the ground. Aviation engines can be separated into two groups: reciprocating engines and turbine engines. While most airlines and corporate airplanes use turbine-powered airplanes, general aviation and training aircraft are equipped with reciprocating engines. Reciprocating engines have several cylinders. Inside of those cylinders, fuel and air are mixed, compressed, and then ignited. As this fuel-air mixture is ignited, its explosive force moves the piston inward. These pistons are connected to a crankshaft, and when the pistons move in and out, that causes the crankshaft to rotate. The propeller is connected to the crankshaft, so as the crankshaft rotates, so does the propeller. The cylinders undergo a continuous four-stroke cycle. The four strokes are called intake, compression, power, and exhaust. The first stroke, the intake stroke, is when the piston inside the cylinder moves away from the cylinder head. As the piston moves away, the intake valve opens, and the fuel-air mixture is sucked into the cylinder's combustion chamber. Once the piston has reached the base of the cylinder, it's time for the second stroke, compression. During this phase, the intake valve is closed, and the piston reverses direction, moving back towards the cylinder head. This compresses the fuel-air mixture since it has nowhere to escape. Once the piston approaches the top of the cylinder, we begin the third stroke, power. Two spark plugs at the head of the cylinder each let off a spark, which ignites the fuel mixture and makes it combust. This controlled explosion pushes the piston back inward towards the base of the cylinder, which in turn rotates the crankshaft, and therefore the propeller. Finally, we reach the last stroke, exhaust. During this phase, the exhaust valve opens, and the piston moves back towards the cylinder head, pushing out the combusted gases commonly called exhaust. Then, the process starts all over again, repeating the process thousands of times every minute. On a typical four-cylinder engine, each one of the cylinders is in the middle of a different stroke. That way, one cylinder is always in the power stroke, and the engine is able to keep the crankshaft rotating, thereby allowing the remaining cylinders to go through their respective stroke. As we just saw in these four strokes, there are two valves at the head of each cylinder that open and close to allow the fuel mixture in and the exhaust gases out. But what controls those valves? That would be a camshaft. The camshaft is a rotating cylinder situated above the crankshaft with various oblong lobes protruding from it. These lobes push on rods that connect to each valve, pushing them open. The valves are spring-loaded and will return to the closed position as the camshaft lobes move away from their respective rod. Getting the valves to open at the exact moment is very crucial for the engine to operate. Because of that, the camshaft is geared to the crankshaft so they will remain synchronized. The camshaft is geared to spin half as fast as the crankshaft. This results in the valves opening twice during the four-stroke cycle. Now, how do we get the fuel and air into the cylinders? It's simple. The induction system. Inside of the cockpit of most general aviation aircraft, there are the throttle and mixture controls. The throttle controls the amount of fuel and air that go into the cylinders, while the mixture controls how much fuel is mixed with the air. In simple terms, the mixture controls the ratio between fuel and air. Typically, for every fuel molecule, there are 15 air molecules. The mixture adjusts the amount of fuel necessary to maintain this ratio. The throttle, on the other hand, controls how much of that ratio is let into the cylinders. The more the throttle is open, the more fuel and air enter the cylinders, and therefore, the more powerful the combustion will be, making the engine run faster. The air that is part of the fuel-air mixture enters the system at the air filter, usually found in the front of the airplane. Once the air passes through the filter, it is metered and sent on its way to the cylinders. The fuel, on the other hand, is housed on board the plane, typically inside of the wings. Just like the air, it is metered and then sent to the cylinders. There are two different potential systems used that can control the fuel-air mixture: the carburetor system and the fuel injection system. Most modern airplanes are equipped with fuel injection systems, so we'll spend a little more time on that, but it's a good idea to still review the basics of a carburetor. The job of the carburetor is to mix fuel with the air that gets sent to the cylinder combustion chambers. Fuel arrives at the carburetor and sits in the float chamber, waiting to be used. To the side of the float chamber is the venturi, which is where the air passes through. As the air passes through the venturi, its velocity increases, which causes the pressure to decrease. Towards the bottom of the venturi, we find a fuel discharge nozzle, which is located near the area of low pressure. This draws the fuel out from the float chamber through the nozzle and mixes it with the air. Just past the venturi is the throttle valve. This controls how much of the fuel-air mixture is being sent to the cylinders. In newer airplanes, fuel injection systems are installed, which have many benefits over carbureted engines. Fuel injection engines reduce the amount of fuel required, increase engine power output, and allow for the precise use of the fuel. Rather than having a carburetor, a fuel-injected system is split up into different components. These consist of fuel pumps, a fuel control unit, a fuel manifold valve, and finally, fuel discharge nozzles. The fuel pump pumps fuel from the fuel tanks into the fuel control unit. Then, the fuel control unit regulates the specific amount of fuel needed based on the mixture and throttle settings. The fuel then gets sent to the fuel manifold valve, where it is dispersed and heads to the nozzles of each cylinder. This time, the fuel does not mix with the air until immediately before entering the combustion chamber. Now that we've discussed how we get fuel and air into the cylinders, let's talk about how we get that mixture to ignite. The ignition system is what provides the spark to the mixture. The major components of the ignition system include the magnetos, the spark plugs, wires, and the ignition switch. Just as its name implies, a magneto consists of a rotating magnet that generates sparks of electricity. The spark that is generated is independent of the airplane's electrical system. That means if the airplane's electrical system were to fail, the magnetos would still be able to generate sparks for the engine to run. The energy generated from the magnetos is sent to the spark plugs. The spark plugs then release that energy, which ignites the fuel-air mixture, creating power to turn the propeller. Most airplanes have two magnetos, multiple sets of wires, and two spark plugs per cylinder in order to increase efficiency and reliability of the system. If one magneto fails or one spark plug fails, the engine will still run. However, power output will be slightly reduced as the engine is operating less efficiently. The last component is the ignition switch, which is the pilot's way of controlling the magnetos. In most general aviation aircraft, the switch is labeled off, right, left, both, and start. If the switch was to be placed off, then the magnetos would not be able to power the spark plugs. Therefore, the engine would not be able to run, and it would turn off. If the switch was placed in the right or left position, then only that respective magneto would be powering its spark plugs. If the switch was positioned on the both selector, which is its normal position for flight, both magnetos would be powering the spark plugs. Finally, the start position. This engages the starter, which turns the crankshaft to start the engine. In the cylinders, the spark plugs ignite the fuel-air mixture, moving the piston in the power stroke. However, there are a few abnormal conditions that can affect the performance of the engine. The first one is called detonation. Detonation is the uncontrolled explosive ignition of the fuel-air mixture inside of the cylinders. It results in high temperatures and pressures, which can cause cylinder damage. Detonation can happen for a variety of reasons, including using a lower-grade fuel than what is recommended, high power settings with the mixture set too lean, or climbing too steeply with cylinder heads not cooling appropriately. If detonation is occurring, the pilot should reduce the power and increase the mixture, which will allow for better cylinder cooling. Another issue that can develop is pre-ignition. Just as you'd expect, pre-ignition is simply when the fuel-air mixture is ignited prior to its normal time. This phenomenon usually occurs because of a lingering hot spot on the cylinder wall, usually caused by a carbon deposit that is hot enough to ignite the fuel-air mixture. Even when the engine isn't detonating or experiencing pre-ignition, the temperature of an engine can get quite hot. Like car engines, airplane engines have a cooling system in order to prevent engine damage or engine failure. There are two major ways we cool our engine: oil and air. Oil passes through an oil cooler and proceeds to not only lubricate, but also cool the engine. As the cool oil touches the hot engine, there is a heat exchange, meaning that the oil becomes warmer, but the engine cooler. Then, the oil returns back to the oil filter and oil cooler, and the process starts over. However, we also use air to cool our engines. As the airplane flies through the air, outside air flows through inlets usually found on the front of the airplane like the Cessna 172. This outside air is colder than the engine, so as the air flows over the engine, it cools it in the same manner that the oil cools the engine. This method of cooling can be severely restricted, however. When the airplane is running at high power and at very low speed, such as when climbing, airflow is minimized, causing higher temperatures. The last step in the four-stroke cycle is the exhaust. The exhaust system has a dual purpose in most general aviation airplanes. As expected, the exhaust system does allow the hot exhaust gases in the cylinder to escape the engine in a quiet manner. Additionally, as we'll talk about later, the exhaust system also provides heat to the cabin. Now that we have a better understanding of how an engine basically works, we will examine what creates the thrust for the airplane to fly. Remember that as the combustion occurs in the cylinder, the pistons rotate the crankshaft, which directly drives the propeller. The propeller, when closely examined, is actually twisted. This is simply to create equal thrust along the propeller blade. Since the propeller rotates around its hub or center, the further the propeller extends out of that hub, the faster it spins. To create equal force throughout, manufacturers twist the blade. There are two major types of propellers: fixed-pitch propellers and constant-speed propellers. The Cessna 172 is equipped with a fixed-pitch propeller. This means that the pilot cannot manipulate the propeller blade. It is installed onto the airplane and will always remain exactly how it was installed. An airplane equipped with a fixed propeller only has the throttle to control the engine RPM and therefore propeller RPM. A constant speed propeller, such as the one on the Diamond DA-42, is more efficient than a fixed-pitch propeller. With a constant speed propeller, the pilot can adjust the blade angle of the propeller to obtain maximum performance for different conditions of flight. Airplanes with a constant speed propeller are not only equipped with a throttle, which still controls the power created by the engine, but they are also equipped with a propeller control. This control, which is usually blue in color, allows the pilot to change the RPM of the propeller instead of just based on the engine's output. The reason this propeller is called constant speed is that when throttle movements are made, the RPM, or speed at which the propeller is rotating, will remain the same. This is accomplished by rotating the angle of the blades, which allows them to deflect different amounts of air.